And we asked the question, we're going to ask it in parts of these lectures, how small can we make a satellite or planetary probe? Looking at different kinds of timescales, what are these going to become? Cost and mass to orbit favor making them small, definitely. And we already have microsats as an example. They're quite established now. We'll see an evolution also from, large multi-purpose platforms to swarms of satellites that can do function. Swarms of smaller satellites. And we'll look at that during this talk. But if you want to send stuff really far away and do it quickly, the only choice we have is to scale the mass way down. Just don't send much stuff at all and give it a really strong kick. The extreme version of this maybe is the proto-molecule on The Expanse. I'm a real fan of that show. You can see my background. It's great science fiction. And there they talk about a single molecule that can self-replicate and have a purpose. Biology is kind of an example. They take it to an extreme. We're not there yet in our technology, for better or for worse. But we can still talk about scaling things down very small and then sending them far away. People are bold enough now to suggest sending chip scale planetary probes to Proxima Centauri and do it within a good number of our lifetimes. It's just such a bold idea, so extreme, pushes technology in so many ways. It's so exciting. So with that in mind, I'm going to turn it over to Juliana to introduce the speakers. Thanks.
Well, let me be very speedy here. I'm a PhD student, one of the head PAs in Adventures in Sensing Group, and I just want to say that on the theme of small sats, I think we are so lucky to have Professor Zach Manchester, Professor Dave Miller here. They were the first two people that came to mind when I thought about people doing interesting work in this area. So So Zach, we've actually hosted Zach once before when he was a postdoc at over at Harvard, and he's done a bunch of interesting work. He launched he designed and launched satellites in a project funded on Kickstarter, which was definitely a first. And he's now on the advisory board at Breakthrough Starshot. He also, his team won a NIAC award last week. For those of you who may be familiar with the NASA Advanced Concepts grant. So maybe he'll touch on that. And now he's a professor at Carnegie Mellon, working on very interesting questions in the area of hardware and control algorithms for robotic swarms. And then after Zach's talk, we'll switch over to Dave Miller, who may be familiar to a lot of you in the audience because he's a MIT professor on leave running the Space Systems Lab. And Dave and I have worked together in the past on a wafer scale satellite engineering project, which is very much in the spirit of this lecture. But now he's calling in from Aerospace Corp, where he's a VP and CTO running their X team, which is a bit like JPL's X team or Google's X team, which may be familiar. And he's done a lot of interesting work in the area of distributed spacecraft, reconfigurable spacecraft, very well known for the Spheres project, the autonomous nodes on space station. So very interested to hear his take on the future of small sats. So I'll pass it over to Zach at this point, and we'll take it away. And I'll just also note that I'm really excited by this audience. We have a lot of people calling in from Lincoln Lab, professors and students from multiple departments at MIT and the Media Lab. So if anybody wants to introduce themselves over chat as the talks are kicking off, please feel free.
All right, so let me do the screen share thing here and cross our fingers that Zoom cooperates today. All right, are we in business? Does everyone see my slides? All right, good deal.
Looks good.
Okay, so first I'd like to kind of kick things off with a little bit of a kind of thought experiment that I like to pose when I give kind of general audience talks on this stuff. What if flying a satellite costs less than your smartphone? So why don't we just kind of ponder this, and then maybe at the end when we kind of do the Q&A, we can pick this up a bit. So I'd just like to see that thought. So here's a few things I would do if I were in charge. So one is ag. It turns out ag is the second largest consumer of space-based data, and so tons of Earth imagery gets used to sort of plan fertilizing and planting of crops. But it's only really done right now in the sort of first world countries because the cost of the data is prohibitively expensive for sort of places that maybe could actually benefit from it the most in sort of developing countries. So this is one area where I think if we had cheaper satellites and cheaper access to this data, you could do a lot of good, especially in light of trying to use less resources and climate change and all that. Another obvious one is weather forecasting. It's a huge user of space-based data. And right now, people might be aware there's kind of we have an aging fleet of weather satellites, and there's sort of newer techniques for collecting weather forecasting data that we kind of would like to have more satellites on orbit able to do this. Another one that's sort of gotten really big in the last few years on small sats is Earth-based imaging. I'd just like to point to these. These are some really cool pictures from Planet Labs, a startup that has a fleet of like a couple hundred small sats on orbit right now doing Earth imaging. The first one on the left is a picture of a tornado's path in Wyoming. This is like 2 summers ago, I think now. And they basically caught the tornado in real time. The second one is a picture of Kathmandu right after the Nepal earthquake that happened a couple of years ago. And in both cases, what I want to emphasize is that these are sort of lucky shots that were captured like sort of right after or as these events were unfolding. Right now, the revisit times, even for planets constellation, are on the order of like once a day. And so the time, what that means is the time it takes to get another picture, an update of a particular spot on the Earth is order a day. And if we could have more satellites, in principle, we could see these things unfold sort of in real time for things like disaster response. Last one, which is one that's kind of near and dear to me, and is one of the places I got into this whole game a long time ago, and an area we're still pushing on is wildlife tracking. So in particular, birds. I did my undergrad and PhD at Cornell, and there's a fantastic lab there called the Cornell Lab of Ornithology that's one of the world leaders in ultra small wildlife tracking tags. And the holy grail for a lot of these people is global tracking of migratory species like these birds. The problem is the birds in particular, they migrate over the widest range, but they can carry the smallest payload. So the tags for a lot of these migratory birds need to be on the order of a gram, and they need to be long-lived, and they have to work anywhere on Earth because these things go all over. They go from pole to pole and things like this. So we can't do that with current satellite tracking technologies, and it'll take both really advanced tag technologies on the birds and dedicated satellite receivers to receive these really weak signals. So this is kind of another thing that we've got some interest in. Okay, so some crazy ideas, maybe some not so crazy ideas. Have a think about it. So I'll dig into kind of what I've done over the last few years and some of what my lab's still working on. This is, as far as I'm aware, the world's smallest spacecraft. It's a single printed circuit board. It weighs about 3.5 grams, 3.5, 4 grams. It's 3.5 by 3.5 centimeters, a couple millimeters thick. The devices on here are pretty much all commercial off-the-shelf standard stuff. There's a microcontroller, a small radio transceiver, a gyro magnetometer, sort of sensors that are in your smartphone, a small solar panel, and an antenna. So I sort of initially worked on this stuff as an undergrad, and then stuck around for a PhD to keep doing it. And the first time we ever flew these was on the second to last shuttle mission, actually, STS-134, on an experiment called Missy 8 that went up to the ISS. This was a material science experiment that one of the experiments pulled out of at the last minute. And my advisor got a phone call saying, hey, do you have anything you can put on here that you want to fly? Oh, by the way, we need it in 48 hours. So this prompted, a couple sleepless nights of us putting the boards together and potting them in epoxy and then driving them down to get them integrated. This is when they were deployed on station. So this was a spacewalk, right? And I love these pictures. This is a picture taken out the cupola on the ISS of 2 astronauts on the spacewalk. And if you notice, the astronaut on the left here is actually holding a camera. And this is that second picture from the first astronaut. So this is a picture of an astronaut taking a picture of an astronaut taking a picture of installing this experiment. This is that last picture showing our little boards up here on the ISS. So these went up, unfortunately, because of where they were mounted, and we had no control over this. And as I said, it was at super last minute. These were mounted on the anti-nadir side of the ISS, which means they were sort of facing out into space with a big hunk of space station between us and them. So we weren't able to get any signals off of them, but they kind of hung out in space for about 3 years and came back down to Earth, and we got them back. physically got them back. So we were able to test them, and sure enough, we stuck them under a lamp in the lab, and they powered up and started transmitting right away. So it was kind of an interesting first, kind of proof that this sort of cheap COTS hardware could survive, at least in low Earth orbit, for long periods of time without suffering any major ill effects. So after this happened, as I was kind of getting going in my PhD, we kind of decided that we wanted to really fly these things as real free-flying spacecraft. And inspired by, I guess, the kind of, nascent CubeSat scene at the time, this was about 10 years ago now, and also a NASA program that started called ELANA, which stands for Educational Launch of Nanosatellites, which, by the way, is still around and still a fantastic program that awards free CubeSat launches to university teams that anyone can submit a proposal to. I wrote a proposal to this program as a grad student, and was lucky enough to get awarded a free CubeSat launch. So we decided we were going to pack about 100 of these little tiny sprites or chipsats into a sort of CubeSat mothership and fling them out in low Earth orbit like this. This led to a whole, interesting saga that we could get into at some point that I'll spare you the details on. Needless to say, some particular federal agencies were not big fans of this idea for maybe somewhat obvious reasons having to do with tracking and debris. And it took quite a long time to actually pull this off. We were finally able to do that a couple of years ago now. This is KickSat 2. There's some more details in that, in KickSat 1 versus KickSat 2. This was just about exactly 2 years ago. This was like March 2018 when this all went down. I got to watch this launch out at Wallops, which is pretty awesome. If you have a chance to go down there, you get to watch this from the beach right across the water. And here's the actual final images of KickSat 2 on orbit getting popped out of the deployer. You can see it there. There goes our satellite. It's in space. And a couple days after this video was taken, we were able to send a command up to that sort of CubeSat mothership to deploy all the little guys like you saw in that sort of artist impression. And I was down here at this place on the right, which is the Stanford dish out behind Stanford's campus, sort of in a little shack down here, sending up the commands and then listening for the ChipSat signals. And this is a live screenshot of our ground station receiver of what's called a waterfall plot, showing the signals coming in. And these yellow lines are all little signals from the ChipSats kind of recorded live. These are the first ever ChipSat signals kind of received from space, and the first time these little guys actually worked on orbit. So we did this once. Probably won't be doing it again anytime soon because of the insane hoops we had to jump through to do it, and the fact that there's not a lot of support in the federal government for doing this kind of stuff, and there's a lot of concerns about debris and stuff like that. But some of the things that kind of came out of this that we're still working on that I think are pretty interesting, I'll kind of highlight now. Some of the research questions we're kind of playing around with in my lab. One is actuation on really small satellite platforms. And when I say actuation here, I don't mean necessarily orbit control, so like thrusters for actually changing your orbit, but rather attitude control, which is sort of rotating the satellite around and pointing at things, which is a key kind of core functionality that you need on just about every satellite for pointing your solar arrays at the sun, pointing antennas at ground station receivers, pointing sensors like cameras, et cetera, at targets that you want to image. So it's a really core thing that you need to do on most satellites. And this is a plot that I threw together a while back of the fraction of the spacecraft taken up by the attitude control system or the actuators required to do this kind of pointing. Typically, these are things called reaction wheels or CMGs. This is a picture of one here. They're basically flywheels. And the idea is due to conservation of angular momentum, you spin the flywheel one way and it spins the body of the spacecraft the other way. This picture is of one of these actuators from the ISS. So if you think about the ISS, this thing's a couple of football fields across. It's huge. These actuators are only a few feet across. They're not that big. And as a fraction of the overall spacecraft, they're really small. Only about 0.25% of the whole spacecraft, of the whole ISS, is taken up by these actuators. If you go down to smaller and smaller spacecraft, so you see this interesting trend. So for a geocommunication satellite, like TV broadcast satellite, that kind of thing, these actuators take up a couple % of the satellite, and those things are about the size of a commercial jet. They're pretty big. Something like a LEO Earth imaging spacecraft, there may be 5 to 10%. And now when you get to this CubeSat scale, these sort of the mothership satellite that I showed you before, where things are like on the order of a couple kilograms, these actuators are taking up anywhere from a third to a half of the satellite, and you're running out of room to do anything in terms of payload. And the trend is kind of not great, right? As you go smaller than that, even at the CubeSat scale, it starts to be prohibitive. And much smaller than that, certainly down to this chip size scale, these kind of mechanical actuators where you're spinning flywheels around don't really scale down and sort of end up taking up the whole satellite. So we're kind of interested in looking at alternatives to this classical setup. One that we've played around with a bunch are actuators that are not uncommon. They've been used on spacecraft for a long time, called magnetic torque coils. The idea here is you have basically a few electromagnets. You run current through them, generate a magnetic moment, M, and that magnetic moment you generate interacts with the Earth's magnetic field, which is the B here, to generate a torque. So this sounds great, right? And these can take up very little space. In fact, we can make them into the flat solar panels on the outside of the satellite, so they don't take up any internal volume at all. The issue is, here's what that torque looks like. It's M cross B. And what you note here is I can generate any M I want by having a nice array of these electromagnets, but the torque I get, I can never get a torque parallel to B. I only ever get 2 degrees of freedom worth of actuation. So that's a problem, and that's why these haven't been used for full up pointing before. So we've come up with in the last year or so is basically a scheme that takes a map of the Earth's magnetic field and knowledge of the satellite's orbit to kind of solve a planning problem. And this is, don't worry about the math here, the picture is the important part. Basically, we plan ahead by 4 or 5 minutes, knowing where the satellite's gonna be and knowing where that B vector is gonna be. And because the magnetic field of the Earth is actually complicated and varies spatially, because the satellite's moving, that B vector is gonna move around. And if we're clever and plan ahead, we can basically do whatever we want over the span of, say, 4 or 5 minutes in just about any orbit that you would care about in low Earth orbit, at least. So that's kind of fun and lets us sort of get around some of these limitations. Another idea that we were playing around with too, that I kind of like, that's sort of a little bio-inspired, is looking at animals that are on similar size scale to our satellites. You got things like geckos that can actually do really a great job at 3 degree of freedom attitude control by whipping their tails around. And these guys, by the way, are 3 or 4 grams. They're on the same size scale as our little satellites. As a fun plug, humans could do this too. This is a video taken from the shuttle middeck back in the 90s of people wiggling their arms and legs around to do this. So again, it's conservation of angular momentum, but rather than wheels, you're kind of dealing with tails or arms or wiggly appendages. So why is this advantageous compared to the wheel thing? It turns out, basic physics, the inertia here, inertia scales with length squared. So if you have a deployable arm or appendage, you get a big advantage compared to a wheel that's kind of buried inside the body of the spacecraft. So here's a cartoon version of this that we've kind of cooked up for something like a CubeSat that has these deployable booms. And we think we can actually do a really good job of ultra fine pointing, like really high precision pointing with a system like this, where these booms can move very slowly rather than having to spin around at hundreds of RPM, and you get this big length squared advantage in the inertias of these things versus the wheels. Okay, so actuators, pointing. Another thing that we're playing around with that's kind of fun is how to do navigation, or at least relative navigation, on very small spacecraft with very cheap, low-cost sensors. So in particular, the sensors that are easy to come by that we already have available to us are RF 2A time of flight ranging sensors. So with the radios we already have on these tiny satellites, we can actually get fairly accurate, and accurate, I mean sub-meter, like half a meter or so, range measurements by just measuring the time of flight of the signals between these guys if they're talking to each other. The problem is there's an inherent ambiguity in this. If you have, say, a handful of these guys and they talk to each other and they get ranges, let's say this picture with 3 satellites, so I can fix the distances between them like that. But there's this inherent ambiguity where I can sort of rotate or translate the whole collection of satellites around, and the ranges don't change, right? So we need some extra piece of information. Ways that you might think about getting around that: one, you need some kind of external reference, right? So one way might be to reference some other satellite, which is sort of a GPS kind of esque solution. Another one would be to reference some kind of ground station. And I should mention, this is sort of looking ahead to doing sort of this kind of thing around other planetary bodies where we maybe don't have GPS, right? and maybe you don't want to always be talking back to the Earth. So in this cartoon picture, we're talking about the moon maybe. So here's another idea that we're playing around with. It turns out the moon in particular has a very lumpy, very irregular gravitational field that's very well mapped. And that lumpy irregular gravity field affects the motion of these little satellites if they're in orbit around the moon, and it affects those ranges. So it turns out if you orbit the moon for a while and sort of collect a whole bunch of this range data over time, and you have a good map of the lunar gravity field that can sort of explain these small variations in range measurements as you accelerate, as you move around, and sort of are subject to different gravity, you can use that to actually localize and back out your position over time with a good gravity map. So we're playing around with some of these ideas on a mission that actually just launched called VREX in collaboration with NASA Ames, which is 3 of these little 1U CubeSats, so it's about a kilogram, 10 by 10 by 10 centimeters, sort of palm-sized satellites. These are in low Earth orbit. Earth does not have a sufficiently lumpy gravity field to do this. But we're collecting range data from these guys and sort of demonstrating some of the concepts on orbit. Okay, a couple final plugs. One is that we've put a lot of work in my lab to designing sort of satellite hardware for low-cost satellites, and we've open sourced all this stuff. So if anyone's interested, we have a full CubeSat avionics stack, basically everything you need to build one of these small satellites. That's open source. It's been radiation tested. It's flown a couple times on both the KickSat-2 mission and the VREX mission I just mentioned. And it runs Python natively, so it's easy to program, which is a big thing for us because we get a lot of sort of aero mechanical type students who don't necessarily have expertise writing embedded C code and debugging microcontrollers and JTAG and all that fun stuff. So yeah, we're pretty excited about this. We'd love to have more people use it. We're trying to get it out there and get other schools to play with it. We've had a lot of interest from capstone programs at various universities. And I ran a capstone around these boards last year, right before the lockdown started, that got kind of interrupted at Stanford. So yeah, check these out. They're on GitHub if you're interested. And then lastly, as was mentioned, looking forward a very long way, perhaps, towards getting these things farther away from Earth as a project that I'm on the advisory committee of called Breakthrough Starshot, where the vision is to take sort of gram scale satellites like these tiny chipsats that we've been talking about and take advantage of their very small mass by mounting them on some sort of solar sail and using a big laser to get them going really fast and potentially accelerate them out of the solar system and toward other interesting destinations. So I'd be happy to talk about any of this. And quick plug for my students who do all the hard stuff. First up here is Max, who's the lead developer of all our hardware, the PyCube stuff. This is Kevin Tracy, who's kind of our controls guy, who's doing a bunch of the magnetorquer attitude control stuff and the wiggly appendage attitude control stuff. And then Brian and Taylor down here are the main developers of our numerical optimization tools that we use to solve these control problems. And yeah, that's kind of, that's it for us. And I'd love to open it up and take questions and stuff and hear what you guys have to say about this stuff.
That was an awesome talk. You covered so much ground in a short time, but I think it really shows all the potential here. So let me check in with Dave. Do you have to leave, Dave, right at 2 Eastern? Are you on a tight schedule here?
Well, I could probably go until 2:10.
2:10. Okay, that's actually very helpful because that gives us a little bit of time here to take questions. So if you have a question, you're welcome to either speak up, put it in the chat, and I can read it aloud. But
I'm trying to see the chat.
I can ask a quick question while it's quiet. It's great stuff. I'm wondering, Zach, about your tails. I mean, you can do momentum transfer a little with proof mass, motion like you do now, a little bit to get it to move. Of course, you can't build up any bias. It's only all the things
right.
moving. But you also can extend the boom for gravity gradient stability. If you're in orbit, LEO, I mean, if you guys thought about that, where if you wanted to be Earth fixed, you could maybe exploit that.
Yeah, absolutely. If you just care about Earth pointing, I think you're absolutely right. The gravity gradient thing is a pretty good way to go. For those who don't know, this is a trick where if your spacecraft is long and dumbbell shaped, it will naturally settle into sort of have the long skinny axis oriented towards the Earth all the time passively because of this thing called the gravity gradient effect. So yeah, that's totally a reasonable thing to do. It's surprisingly tricky to get that to work in practice too, though. It's sort of, you need good damping, and you need a way of initially getting yourself into the right attitude and sort of damping out oscillations. So you still need some control, it turns out, and it's hard to make those things work. Like you need a long boom and stuff. So but yeah, it's totally workable. It's been done, going back to the 60s successfully. So I think it's also a reasonable thing to do.
And how does your radio talk? I mean, what kind of bandwidth do you get off that little radio?
So there's a couple of things going on there. The older stuff, this was 10 years ago, pre-LoRa and all these nice, spread spectrum things. So that was a custom direct sequence spread spectrum thing that I hacked together on an existing chip radio and did all our own signal processing and all that kind of stuff. Now there are, because of the growth of IoT, there's actually like commercial chips you can buy that do very similar things, and LoRa being the prime example. And so we use that stuff now basically because it's really good and it's baked into the chip. But yeah, the bandwidths that we run on the VREX mission, so the big limitation is actually what we can license practically. And I forget what the actual legal limit is in UHF, but it's something like 100 kilohertz is the bandwidth you can get as an amateur. So we run basically within those limitations.
Anyone else sitting with a question? Want to jump in?
Yeah, hey Zach, this is Clayton Baumgart at Lincoln Lab. I'm curious about the trajectory optimization and path planning for magnetorquer only control. Do you have difficulty combating environmental torques with that method of control, or is that something that not applies to a 1U semi-symmetric spacecraft?
So to be honest, yeah, we haven't done that in orbit. We would like to. We have some possible schemes for maybe trying that on this VREX mission if we sort of check all the nominal mission success boxes early enough and have some bandwidth left to do it. Yeah, I think part of that is, yeah, like you said, that's a pretty symmetric design, and there should be minimal disturbance torques. In general, it's underactuated, right? So you're only ever going to get these 2 degrees of freedom. So if you have a disturbance kind of nudging you and it's torquing you in that third axis that you don't have control over, you're going to have significant error. And I think practically speaking, if you were to do a really good job at this, you'd probably be looking at like a few degrees level of pointing accuracy. So it's not going to get you the same kind of pointing stability and accuracy that you can get out of a full sort of reaction wheel array, but you can do full 3-DOF pointing. It takes about 4 minutes, we found, by doing like worst case, we kind of sampled over low Earth orbits at a roughly 500 kilometer altitude, all kinds of orbits, and looked at this. And at worst case, it's about 4 minutes to do an arbitrary slew. So that's the kind of time scale you have to wait for some arbitrary reorientation.
Great, thanks.
I had a question about the breakthrough Starshot mission. So what do you envision being the sensors that it would carry? Like, what's it hoping to detect if it goes into interstellar space, if you can only put these tiny little embedded sensors on it?
Yeah, I don't think anyone has a real honest answer to that. I think the generic answer is cameras. And maybe, like a camera is what people like, is sort of the dream. And then, it's quite easy to do various other flavors of small sensors for things like magnetic fields. I don't know what else you might want, but I think the notional idea is that there would be some kind of imager on there, some small camera. And you might argue, the resolution on a camera that you could fit on there, with diffraction limited optics, et cetera, is going to be really bad. But if you work out the numbers for trying to take the same image from an Earth-based telescope, it turns out like an iPhone camera on something like this flying by at 1 AU from an exoplanet is better, dramatically better than you could ever do with an Earth-based telescope. So even like an iPhone level camera is a huge win.
Nice, thanks.
Sorry, I got a quick question just about the navigation. You mentioned the satellites can leverage the magnetic field of the moon. So what if the satellites are very close to each other and much smaller than the resolution of the map? Will this approach still work? Thank you.
So yeah, so in particular, the thing I just mentioned was the gravity field. And so what happens there, right, you can imagine if there's like a big mass concentration, it's going to exert a stronger gravitational pull. So the simple version of this is if you have two satellites flying like one in front of the other, as the first one approaches that mass concentration, it'll speed up a little bit and the range will increase. And then as the second one sort of goes over it a little bit later, it'll kind of catch up, right? So that basic idea has been used to map gravity fields of Earth and the moon. And this is why we have really high resolution gravity maps. But yeah, if the spacecraft are sort of closer than the resolution of kind of both the range sensors and the map, it's going to be buried in the noise and hard to extract. So yeah, there's absolutely limitations to all of this stuff. You mentioned magnetic field though. It's also similarly possible to navigate based on magnetic field sensors if you have a good map of the planet's magnetic field.
Zach,
Thank you.
Do you have to leave right at 2?
I do have another meeting at 2. Yeah.
Okay. All right. Well, we'll see if we have time a minute or two at the end, but I think for now, pass the torch over to
Sounds good. Thanks.
Dave. Thank you again.
Hey, Juliana, can you hear me?
Loud and clear.
Great. So first I have to apologize. I got about 3-day notice for this talk. And so I can't really get my aerospace material through public release, but I'd be happy to come back at a later date and tell you all the stuff that we're doing in small sats at Aerospace Corporation. The other, I want to give a shout out to MIT. When I saw the Perseverance rover landing, amazing how many MIT students made that landing happen. It's MIT is EDL, and it was great to see. The other thing I wanted to mention, Zach brought up a really important point about agriculture being one of the big users of space-based data. NASA actually, at least when I was at NASA in 2014 through 2016, NASA was giving away a lot of our Earth science data for free to various nations around the world for use for things just like that. And in fact, for under-resourced countries, there's a program called Severe, where we not only share the data, but we also go into those countries, or NASA goes into those countries and helps them understand what the data is telling them. And so I just want to make that point. A little bit about aerospace. I have to give the plug there. In my office, we have it's not X Team, it's X Lab. Sorry, Juliana. And what X Lab is, that's our prototype and our CubeSat program. We do have something like JPL's X Team, which is called the CDC for Concept Development Center, and we do a lot of architectural design for various missions for the customers. The X in my office is X Lab. We've actually do a lot of work with small satellites. We've launched 33 satellites over the course of since 2000, and 25 are still active, 15 are still in mission. We launch about 4 a year. That's nowhere near what the ChipSats are, but what's kind of unique is every single one that we launch is very unique. And so we only do one-offs, if you think of it that way. And again, I'd be happy to talk more about what they do, but they really span the area of space weather sensors. We've been launching them since actually the 1960s. Compact laser comm, deployables, infrared and spectral imagers, different kind of propulsion techniques, proximity operations, advanced RF antennas, and things like that. The last thing I'll mention about aerospace is the reasons why I came to aerospace. I find it to be a very collaborative organization because we do work with big and small industry, as well as a number of government agencies and actually international partners. It's a very exciting time in space. So for a space cadet like myself, it's nice to, it's interesting to see what's going on. And I'll tell you, exciting is really a two-edged sword. There's all these new entrants into the field, the small satellites, the new launch vehicles, that's very exciting. But it's also with all that, there you get a lot of congestion and a lot of players, and so it can also be challenging to operate in this new environment. So the action is happening now. And the last one is you get to see it all. And this really blew me away, because at NASA and MIT, you get to see different segments of it. But at aerospace, you see the civil sector, which is NASA and NOAA and others. But you also see the US Space Force, you see the intelligence community, you see the Missile Defense Agency, you see international partners. Technology really spans all of that, even though the missions are very different. And it's been a very unique perspective that I find fascinating. And if you're interested in aerospace and you're interested in space, I really encourage you to consider it. So what I was going to do today was give a talk that I gave back in 2015 when I was NASA Chief Technologist. I'm going to go to slideshow mode. Can you still see my slide? This is when I had a nice graphic artist for me, helping me at NASA. So
Good.
I called this talk "Big Ideas Come in Small Packages," and I'm referring to CubeSats here, which is what that robotic arm is holding up, or at least small sats. And I was looking through this, and it was interesting. It's like opening a time capsule from 2015, because things are happening so fast in this field. It was interesting to see what part of my statements actually still ring true today. Some don't, but most do. And I was kind of pleased with that. So I'll go through this. I sort of think we're in the third phase or third emergence of small sats. In the 1960s, it's all we could build. So that's all we could launch. So that's all we built. Then in the 1990s, I remember we sort of had a big a rush to proliferate satellites around Earth in order to enhance global communications. But that attempt came and it went. And I think the major problem there was that it really couldn't compete with terrestrial solutions. And then over this last decade, as shown in the chart on the bottom, there really has been a new emergence in small sats. And you'll see that I'm missing about half a decade to the right end of that chart. And I think the data continues, when you think of what Planet's doing, and ChipSat probably adds a whole bunch there as well. And then you look at Starlink, which really is sort of the upper end of probably what you call small sats. This has just really exploded. So I think in the third time, I think it's here to stay. And I think there are several reasons for that really didn't exist in the first two attempts. First, you've got these ride shares. It's not only that you can ride share on different launch vehicles, but you can also put your payload on other satellites, so you can ride share at the satellite level as well. The second one is technology miniaturization. And the key there is, trying to put big payloads into small packages. You really had to sacrifice performance in the past. But a nice driver, even if it's not ultimately for a small sat, is that it forces the technology to be miniaturized. And that benefits not only the small sats, but also large satellites. There's two others, which is standardization. Setting standards in a business is really important to helping the market grow. And an example of that is the CubeSat form factor. There you've set dimensions, you've set mass, and you now have a supplier base that can develop to provide those kind of elements. And the last one here is encapsulation of risk. I think the Peapod deployer for CubeSats really doesn't get the credit it deserves. It's kind of like, you can scramble the egg yolk inside and still protect the large vehicle that's carrying you. And that's an important thing because the sort of the anchor tenant of the launch doesn't have to worry about your vehicle, your rideshare vehicle breaking. It doesn't pose any risk to them. And that's a really important step for getting these satellites launched. So I strongly feel that shorter cycle times really breed innovation, and the small sat business has allowed that to happen. And so small sats and low cost launch really shorten that life cycle. And that cycle, as shown in that circle on the bottom right, really is from design to development to operation to redesign. So you can go up and test what works in an operational environment, operationally authentic environment, learn what doesn't work, redesign, fly again. The other thing is technology development and flight test almost merge. You know, traditionally you have to have these large environmental chambers to test out your technology. And now it's almost like you can do a ride share and, like what Zach did on the International Space Station, go to the real environmental chamber. And that's the truth. And test your technology there and learn from it. And so the more you can repeat this cycle, it's like practice makes perfect, that the more you can repeat this cycle, the better it gets. So, you know, that faster cycle time, it gets better in launch, in operations, in the technology development, and in a cycle in which we can start thinking about new architectural designs. So I like to think of this as an objective that small sats enable, and that's to create new capabilities by enabling new architectures while strengthening the industrial base. All three of those pieces, I think, are really key to realizing the promise of small satellites. So let me, I'm going to take each of those individually, and I can't change my slide, wondering why here. So to create new capabilities, there are things like resilience. That's the ability to recover from or adjust easily to change. You know, you might have a loss in on-orbit assets, and now your most responsive assets are those you already have on orbit. So you can reconfigure small sats in order to fill in the gaps that are created by that loss. The other thing is, you know, often in the past, these satellites last so long and it takes so long to design them that the mission has changed by the time they get on orbit. But with small sats, we can get up faster, and we can also afford, because you have so many degrees of freedom, think of those as the individual satellites, that as the mission changes, we have ways that we can adapt what we have on orbit to the new mission. And so this brings in a concept which I know several of you have explored, which is real options theory. It's Professor de Neufville's class. Please take it. It's a great class. It's the idea of hedging your bets against uncertain future. So when you have these different degrees of freedom that you can exercise or rapidly put up different capabilities in satellites, you've effectively reduced the switching costs of changing how your vehicles respond to a new mission. And that's the key, one of the key tenets of real options theory. You also get this degree of freedom of inter-satellite redundancy. So if things fail, you can actually exploit redundancy between the satellites. No longer do you have to have reliable on-orbit satellites. You need to have reliable on-orbit capability. And that makes you think very differently about how you design the architecture. Persistence is a big word these days. You'll see, you know, there are different groups working on proliferation, probably to the annoyance of a lot of ground-based astronomers. But there are people thinking about it. And, you know, it's the idea of having longer than usual time without a change in function. So some ideas are do that globally. And you see that with Starlink and other ideas. The other one is do it regionally through reconfiguration and or rapid launch of new assets. There's also aperture synthesis. There's been a lot of money that's been spent on doing sparse apertures. And, you know, I think we're finally getting to working on the technology of it. I think we're finally coming to the time where sparse apertures could really be a game changer in what we do in space. We do it on the ground with things like the Very Large Array for radio aperture synthesis, but in space, it really hasn't happened too much yet. But I think we're right at the cusp of where that can really take hold. And upgradability, we're starting to see this already. In 2015, we really didn't have this, but now we've had the first demonstration of an on-orbit service where Northrop's vehicle repositioned a communication satellite that had run out of fuel. So now we have a ability to to upgrade. Either it could be through launch of new assets rapidly, or it could be the servicing of satellites that are already up there. And we might start thinking about satellites in a modular framework where we can go up and we can replace parts. Maybe we want to replace the processors because they have short obsolescence times, or we want to replace fuel tanks or refuel. Think of drop tanks on aircraft, things like that. There's a lot more ability and perhaps a growing market for doing upgradability on orbit. So then I said, by enabling new architectures. So here I like to think of clusters. So these are local groups of satellites under tight coordination in terms of sensing and possibly likely control. These are things like sparse apertures. There's also things at the constellation level. So these are the proliferated systems or things or constellations that can be reconfigured based on new needs or loss of satellites. And the thing with small sats is you can now come in and say, I want to upgrade the satellites in the constellation. And instead of building a new constellation, like we do block changes with GPS, maybe you can start launching one or two, or every fifth one you launch has a new technology on board. And so now you can have a more seamless upgrade of a capability on orbit than you would otherwise have if you're doing these big block changes. There are architectural concepts like disaggregation, where you actually, instead of having a large satellite that has many different payloads on it doing different missions, you actually spread those out and onto different satellites, in this case without resource sharing. But the nice thing there is you can get around a lot of the sort of design and operational challenges associated with mechanical integration, interferences due to dynamics or thermal or electromagnetics. And if the satellite buses are getting cheaper, this could be a cheaper way to go. You can also start separating things and grouping them based on obsolescence lifetime or mean time between failure or resource demands. Basically grouping modules in terms of these attributes, so that if things with a common obsolescence lifetime, you might want to replace those frequently. So why don't you put those in the same module, and then you can swap them out. Fractionation is another concept. This is the idea of creating a virtual satellite by having several satellites in close formation that share resources. And there's also this concept of reconfiguration, either temporally, how we task satellites, or spatially, maybe how we reconfigure them or hold them information in order to create sparse apertures, or spectrally, actually. You can think of some of these as small satellites providing inspection, servicing, or repurposing and assembly functions, and sort of the worker bees in the beehive of the satellites. So then I think a piece that probably we sort of don't think about too much when we think about small satellites is strengthening the industrial base. So that one aspect is competition. So lowering the lower facility costs encourages new entrants. With the small sats coming on board, we've seen a lot of new entrants coming into the field. It's not the usual sort of big three aerospace industries. The higher production volume stabilizes second-tier suppliers. That's key because for them to stay viable, they need to have a constant sort of demand, and so that they're not sort of 1 month going out of business. Higher production volume and new entrants really lowers cost, and we're seeing that today. The workforce, you need to keep the workforce trained in all the attributes of fielding these kind of on-orbit assets. So higher production volume keeps assembly lines open, and that keeps the workforce trained, the workforce that is there doing assembly, integration, test, those kind of skills. It also provides more opportunities for technology refresh. So if you have an open assembly line, you can surge in case you need to get 20% more production of satellites out at a particular time due to some need. You could also take 1 out of every 10th satellite and put a new technology in it. And if that technology fails, you've lost 1 out of 10 satellites. But then you can learn make the upgrade and put it back into the line. So that's a new attribute that comes in. And that allows, both of these just help to keep the hands-on skills developed and toned so that we can be agile to respond to different needs that we have. Education, small sats, really, a lot of it came out of education. You know, Bob Twiggs at Stanford, used the original CubeSats as an educational tool to teach how satellites work. And now they're doing, they are the bedrock of some very economically viable on-orbit businesses. The other thing is, these small sats are in the financial, and they are within the financial and complexity reach of these educators and these researchers, and that's the key to getting on orbit. The cover charges come way down, and I've already talked about being able to mature technology to higher TRL levels through actual flight, and keeping our skills up. So production agility, open production lines enable on-demand satellite deployment. This adds to architectural resiliency. If we lose satellites, we can replace them. And it also adds to the cost-effective maturation of new technology because you can actually test it out in the full space environment. So when you think about the promise of small satellites, you really need to think about sort of the system aspects of the problem. And it's more than just what's the cost of the production of the satellite, but it's also what's the cost of launch. Can we bring that down? And we have. What's the cost of operations? In the past, when you had many people operating one satellite, having many satellites just sort of proliferates the number of operators. We need to work on that piece as well. And so when you do an architectural analysis of the cost benefit of these systems, you really have to think of a bunch of the attributes you see here. It's not only the architecture, but it's also the design, development, test, launch, et cetera, process. It's how you get new technology put up rapidly and what that benefit can be. And it's the value of having a workforce pipeline that is trained and agile to new needs. So I'm gonna, just to save a little bit of time here, let me step through a couple of these slides. I want to give you one example, which I talked about in architecture, which is reconfigurable to need. If you start in the upper right here, you see two ground tracks. The upper one is like a standard Walker pattern with drifting ground tracks that cover the Earth. I think this is like an 8 satellite constellation in a 60-degree inclination Walker pattern. You can see where the coverage is good in green, and you can see where the coverage is poor. It's down in red. And that's kind of a standard coverage map. You're always going to get better coverage at latitudes corresponding to the inclination of the constellation. But what we can do, if we need enhanced regional coverage, we can, through in-plane burns, we can raise and lower the altitude of those satellites. That's the most efficient way to use propulsion, is for in-plane burns. And we can drop them into altitudes where you have repeating ground tracks. And that's shown in the bottom one here, where it says regional. Now you see that the same constellation has a lot more green coverage over certain regions of the Earth, but it gets that by having no coverage over the white regions. But the advantage here is if you need regional coverage, let's say, those of you that remember the Hurricane Katrina over New Orleans, and then the tsunami in Fukushima, and various volcanoes that have gone off over the globe, we could, through in-orbit in-plane burns, raise and lower this constellation at times that the ground track includes those regions we care about. And now we're going to have a lot more assets going over that region, and we can actually have enough that we can see the temporal dynamics of what's going on with that event. And the issue then becomes, well, we don't know what the future is. Where's the next volcano going to go off? Where's the next big disastrous hurricane? Well, how do you design such a reconfigurable architecture so that you can meet all these possible futures? And that's the concept behind designing reconfigurable constellations. But if you look at the bottom right, what you see is one of these Pareto plots where you got costs on the horizontal axis, some regional coverage performance on the vertical axis. And what you want to have is high coverage, and low cost. So you want to be upper left. And what you see is no architecture gives you all that you want, but what you can see by the family in red, those are all reconfigurable architectures that give you much better regional coverage, regional persistence, so to say, than those static constellations that we are used in blue that we are used to designing today. So this is another architecture. You can start to think about what the cost benefit of these new sort of agile architectures have. And what makes it all possible is low cost satellites so that we can afford to have a high number of them on orbit. So the, there are a number of new functions that come into play with these small satellites. I mentioned them earlier. You got fractionation, sparse aperture synthesis, servicing, inspection, repurposing, where you take old systems and scavenge them for new functions. That could be, has not yet been proven, but it could be a way to be more cost effective than relaunching. But also on-orbit assembly, especially of telescopes. If you look at the James Webb Space Telescope, that 6.2 meter diameter mirror has to be folded up to fit in the Ariane 5 fairing. What do we do on the next big telescope? It's not, we're kind of at the limit of what you can fold up for these systems. And so if, diameter of aperture is everything. And so, we either get a lot larger fairings or we learn how to start assembling these telescopes in space. And that's where these small satellites can come in as assemblers for these larger vehicles, for these larger telescopes. The other thing you sort of get away from is the tyranny of manifest. In other words, we don't have to launch on just the same vehicle. The space station is a classic example of assembly in orbit. Now, it was a lot of human in the loop assembly. We have to start thinking about autonomous assembly if we're doing this out by Earth Sun L2, where a lot of the astrophysics telescopes are going. But, if you can start launching on different the parts on different spacecraft, you do not need to expend all that cost sort of shaving down all the pieces to reduce mass and folding them up carefully so that they'll fit in the fairing. I mean, Perseverance rover and the Curiosity rover spent a lot of money trying to figure out how to fit that all behind the reentry shield. And so, that's a trade that needs to happen, and think about what the role of the small sats will be. So let me just sort of finish off here with sort of a vision, and we'll see if this vision has withstood the test of 5 years. But I like to think of the whole sort of life cycle of space development. You have the design, then you do the assembly and integration and test, then you access space through launch, you do operations, and then you have to dispose of the vehicles once they're at the end of life. And that's kind of a classic cycle. And there's certain ways we do that today. We design for big missions, it's like a 3-year process. Assembly, integration, and test is a very manual process. There's been some improvements in how we do that, how we do the production there. But as Professor Nancy Levinson at MIT likes to say, humans are the source of all error. And the more you can get the humans out of the loop, and you don't do mission assurance of the asset, you do mission assurance of the process, so that that the things that come out of the process are going to work. That's a move we need to make. So let me sort of walk through, think about model-based system engineering. You have high performance computing that's working with a room of domain experts. This is kind of like the Team X or the CDC at Aerospace, to basically not just do a conceptual design, but do a critical design of an architecture and its components, not over 3 years, maybe 3 months, or maybe over a week. If we could do that, you wouldn't have the loss of the experts because they retire or they've moved to another job. You don't have the loss of memory. You're managing knowledge better because it's more of this real-time conversation. You might also carry multiple designs forward. We don't do this today, but you could use multiple designs forward that are sufficiently different each other, but you carry them along at equal fidelity as a hedge against unforeseen issues that always occur. So in other words, when an unforeseen issue comes up with your original design, you might try to figure out how to Band-Aid that, or you go to one of the other designs that is not as sensitive to that unforeseen issue. You might actually, we do data mining, you might actually do design mining. Can you reach back into the designs of previous systems for solutions to the technical problems that you're facing with the current design? That's a nice knowledge capture thing. How we do that today is we bring people in as consultants or out from retirement to bring their wisdom in and say, this is how we did it on the Viking mission. Can we do that using design mining? That would be an interesting idea. All telemetry from orbit is automatically analyzed for symptoms of impending fault and then used to continuously update behavior models. They call this digital twin. And then you can use that to support operations. So instead of saying, oops, we had a fault on orbit, what do we do? We could say, hey, we have a little bit different behavior than we're used to seeing on orbit. What is the likely cause of that difference? And can we operate it differently in order to extend its life, because we're being proactive in how we operate the satellite? Assembly, integration, and test. We could basically, can we print a satellite? Can we build touchless satellites? Get the humans out of the way. Can they be robotically assembled, automatically tested? Instead of Iridium was the first to do this. If you have a fault in a satellite, you don't stop the line to fix it. You throw it away and you go along and then you continue production. Some of this printing could happen on the ground or in space, on site, or at depots at intermediate locations on the transportation network. Launch services can be purchased from a variety of modes like we do with the airline industry, and it's a competitive market. Maybe you want urgency and you need to get there, so you fly direct. Maybe you want proximity to your final location, so it doesn't have to have a tug to move it. You might want to have a high mass, a lot of cargo, or you might want to fly first class and sort of have that nice soft ride or quality of travel. Operations, autonomy and automation are managed in the collective among the computing distributed across the satellites. You can have the human operators. This was already being done in 2015. They're no longer, right there for every moment. They're basically on, it used to be pagers, but the humans are basically alerted or on call when there is an impending fault, and they can come on and be problem solvers. And then disposal. Instead of taking it out to the geo graveyard or re-entering it, we can service them, we can recycle them, we can repurpose them, or consume them as feedstock for on-orbit manufacturing. Planned obsolescence. Right now, these satellites last 15 years because they're so expensive, they have to last a long time. We've broken that paradigm through small sats. Maybe we want to have them be obsolete and disposable, because then we can get technology into the system faster and we can maintain the health of the pipeline. So that's all I have, Juliana. I'd be happy to answer any questions. I've left 3 minutes or something. Sorry about that.
That's okay. Thank you for staying a little bit longer than anticipated, and
Sure.
for joining us today. I know we're personally very curious what you're up to at Aerospace Corp. So we'll have to invite you back with some extra time.
Yeah, I'd be happy to. I just need a little more time to get.
I know that's
a lot in your audience know how that takes time. Sometimes that's the longest item. Yeah.
Indeed. Well, this was a really interesting perspective too, and really glad you joined us. So maybe in your last minute or two, let's try to squeeze in one or two questions. I'll start to connect the talks with the comment you'd left after Zach's talk, which is in relation to high temperature superconductors for satellite formation flight. You can talk a little bit about your work there and.
Okay. I have a talk on that. Let's see. Yeah, at one point I was working with the AFRL, Air Force Research Lab, and they wanted to put a distributed aperture radar on orbit, which was called TechSat 21. This was in the sort of around 2003, 2005. And they were having a problem that they had a lot of propellant they needed in order to hold the formation together, within their, it was sort of about a 0.5 kilometer diameter sort of swarm of satellites. And part of it was just because of these mass bulges in the Earth, like the J2 ablation, was sort of causing secular drift between the satellites. And I realized a lot of the propellant was to hold relative formation. And propellant is good for doing sort of momentum change, but when you're doing a lot of degrees of freedom don't involve momentum change. So what I figured is there a way that without a consumable that we could hold this array together? And so I thought about electromagnetics and the idea that, if you had 10 satellites and you have 6 degrees of freedom, or rigid bodies, let's say, per satellite, then you would have 60 or 60 degrees of freedom in this sort of swarm of satellites. Of those 60 degrees of freedom, 54 of them are fully controllable magnetically. And what you're consuming is electricity, but you got solar rays, so it's renewable. So only 6 degrees of freedom. It's basically it's the 3 translations and 3 rotations of the center of mass are the ones that you need propellant for. And so we came up with a concept for electromagnetic formation flight, and you can control forces and torques between satellites to control all the relative degrees of freedom. And so we started a capstone class to build this, and we took some some iron cores and wrapped copper around it. And we found out it made really good heaters, but it didn't really work very well at a distance, a few centimeters. So then we went out, and there's a company called American Superconductor. We went and got some of their scrap. And then we were able to build coils that would give you like electric propulsion thrust, like 10 millinewtons at separations of 100 meters using sort of 2-meter diameter coils. And that would fit on a satellite. And we were using, the power consumption was very small. And it seemed like a really nice idea. We also realized that now we've got coils. They're like inductors that are in transformers. We said, can we transfer electrical power between vehicles? And the answer is yes. We can also dump momentum to Earth's orbit, to Earth through the magnetic field, because that's how we use torque rods and torque coils in satellites today. We have a lot more authority with these coils. And we actually took it up on the International Space Station and tested it out as well in the full sort of microgravity environment. So there's several companies that have now sort of grown around this. Unfortunately, I'm not, or maybe fortunately, I'm not involved in any of them, but it's nice to start seeing that really catch on.
Yeah, interesting use of advanced materials in spaceflight. So I think you have to go. We could try to squeeze in one more question, or if you need to run, please.
One more question. I'll take one more if you have it.
All right. Anyone want to jump in with a question about?
Or I can come back again and show you about aerospace and answer more questions then. I don't remember MIT being a quiet bunch.
Oh, the world changes on Zoom. It's
okay.
So.
I have a question. This is Mason Black from Lincoln Lab. So you mentioned possibly like carrying forward multiple distinct designs to hedge against unforeseen issues. What's an example that you envision of an issue that you can hedge against like that?
Wow, good question. I think there are sometimes these interferences that happen between like that, where you might have an electromagnetic interference, or you might have a dynamic one, or a thermal interference, and maybe you have several designs in which the layout of the satellite is substantially different. When I say substantially, it'd be interesting to think about what I mean, what that means. Are they in the design space? Am I carrying forward designs that are sort of a set of designs that are full rank in the design space? But that's a good question. I don't think I can answer it at this time. But thanks for stumping me, Mason.
one to think about for the road then.
Yeah.
All right.
I sort of call it the design at the speed of thought. If you can get the human machine interface with high performance computing being fast enough, can you not only sort of pose design questions to the computational assets, but can you get back, free up these parameters, show me optimize a design that gives me performance that is better than what I require, but it can also tell you what's the other family of designs that also give you performance that's better than you desire. And Professor Ollie DeVeck at MIT calls that ISO performance modeling. Once you get the performance where you need it, now you say, well, there must be an infinite set of designs that give me the same performance. And now instead of saying that I need to find a design that meets requirements, I now want to see the family of designs that meet requirements and how are they different from each other. And that helps you to sort of understand what are the sort of family of distinct solutions that meet your requirements. So performance then goes from being something you optimize to something you constrain, and it's called the inverse problem. And then you can, I think there's a lot of, and if the computational resources can give you that feedback sort of in the blink of an eye or at the speed of thought, I think it could really lead to a very different dynamic in the design environment. And I think it would be a beneficial one. Over.
So I'm sitting on a couple of questions myself, but I think we've probably got to let you go if you've got another commitment.
I hope you invite me back again.
We'd love to have you. I'm thinking personally about different applications for reconfigurable spacecraft for disaster response or any other number of.
Yeah, and I think soon to be PhD, soon to be Dr. Charlotte Lowy is on the line. I saw her there earlier. She's working on, I still have grad students, and she's working on reconfigurable constellations. So
oh, great.
There's a lot of, with having so many degrees of freedom available, there's got to be a lot of things you can do. We've just scratched the surface.
Yeah, absolutely.
Yeah, we'll definitely have you back, Dave. Thanks very much.
Great, thanks. See ya.
All right. So at this point, Zach let me know that he actually can stay until 2:30. So this is kind of a transition point in the course where normally the public lectures are about an hour, and then we transition gradually to a Q&A, and then eventually to a more intimate talk with the registered students in the course. So that said, feel free to stick around. And I think
if we're good, I'll take off. Yeah.
I have one quick question, Zach, if you have a second.
Sure.
How do you propose to power these things? I mean, as you shrink the size, you shrink the surface area, so you're going to get less power. Computational requirements are still there. They can come down, but you can do cycle computation, maybe keep stuff off. You have no choice. But especially with Starshot, would you put a little radioactive nugget to do thermo or RTG type stuff? Or what are you guys thinking about for power?
Yeah, the big power challenge is actually comms. The compute is pretty minimal. And yeah, comms is the big one. There are ideas around, like RTG style, nuclear power sources. There's a couple like weirder, more interesting ones for Starshot in particular though. There's this idea floating around that, so I guess the obvious thing to do is always solar. And for Starshot, the idea there is that it will have significant surface area, even if it's very low mass. So maybe there's some way of collecting sort of solar when you get there. The other weird idea though that's kind of fun is that you get heating with the interstellar medium purely because you're going so fast, and that maybe there's a way to harness that with like thermoelectric effect kind of ideas. So that's like my favorite one, but also kind of the craziest.
Yeah, that's interesting. Building on some of Dave's comments around distributed aperture imaging and reconfigurable swarms, is there even the slim possibility of us achieving that level of control on breakthrough nodes traveling at relativistic speeds?
I mean, who knows? I mean, that whole project is very like 30 to 50 years out anyway. So maybe. I love that distributed aperture stuff, by the way, too. And one of the really interesting things there, I think that I didn't touch on in my talk, but that is kind of interesting. The level of control you need to do that stuff, right? Classically, if you want to do interferometric kind of stuff, it goes with the wavelength, right? And so doing it in optical frequencies is super hard, and we're just figuring out how to do that on the ground. but doing it in RF, and in particular, one of my favorite applications for large distributed swarms of these tiny satellites is actually low frequency radio astronomy, where it doesn't go through the ionosphere, so you can't do it from the ground. And the wavelengths are huge, like kilometers. So the level of control and position knowledge you need are easily achieved on these kind of little tiny things. So that one is super fun. And the other comment on that is that at these optical wavelengths, there's been some really interesting work from the machine learning, kind of computer vision world, where these results on achieving super resolution by just like giving like a neural net access to tons of pictures of the same thing. I mean, if you think about it, at some level, the information's there, right? If I take a huge number of photographs of like the same scene at a coarse resolution, and they're like slightly overlapping and stuff like that, there are ways now of stitching those together to achieve a higher resolution final image that are pretty interesting, that don't require this like sub-wavelength level pointing control to actually do classical interferometry. So I think there's a whole bunch of possibilities there.
Interesting. So doing interferometry with a single node, that's
well, not necessarily so maybe, but it's just like if you can take a whole bunch of pictures of the same thing, there might be other ways to stitch it together.
It's a little bit like Mars in 4K. I mean, they're kind of doing that with interpolation and filtering, but then there's light field stuff, which is another version of it.
Yeah, there's a lot of cool ideas out there.
Yeah. Are you familiar with the OFAR project out of Europe?
Yeah.
They're doing the radio.
Yeah.
The distributed radio antenna.
Yeah, I wrote a proposal a couple of years ago with a radio astronomer on like trying to do low frequency interferometry in LEO with CubeSats, but unfortunately didn't get funded. But I still like the idea. I think it's worth trying.
Yeah. So maybe interesting to everyone here. I'm curious about your NIAC, your recently awarded NIAC proposal.
Yeah, I didn't talk about that because it's sort of completely different.
It's not relevant, but
yeah,
it's timely. I figured.
So that idea is it's with a collaborator of mine who awkwardly was left out of all the press releases that NASA put out the other day. A guy named Jeff Lipton, who was a postdoc in Daniela Rusa's lab at MIT and is now an assistant professor at the University of Washington. He's done a bunch of work in mechanical metamaterials and is really into these kind of like tiled, metamaterial structures that can achieve really weird mechanical properties. And in particular, some of the stuff he's worked on involves achieving really high expansion ratios. So you have like some bistable thing that can be sort of pulled apart and can like expand to 100x, its initial, say, area. And you can tile these things and get things that can, the basic idea is the idea of like a Hoberman sphere. If you guys are familiar with the toy, the sphere that you can pull open, right? So that basic idea, but it's come a long way in the last couple of decades, and there's some more recent ideas like that. So the idea is to build structures using those sorts of materials that can achieve expansion ratios such that in a single Falcon 9-ish launch fairing, you could achieve a structure that's like a kilometer across in a single launch and deploy. And then the kind of the pitch for why you would want to do this is for maybe for things like creating artificial gravity, where you would spin such a structure up and be able to achieve like 1G kind of gravity with something that only needs to spin at a couple RPM. So it's at the level where you wouldn't get sick from spinning around too fast. So that was the NIAC.
Cool. Anyone else have questions for Zach or topics to discuss?
So I have a quick question. So I think with both presentations, there's this argument that, having a lot of these small satellites at scales offer many different perks, especially that they can be produced cheaply. But how do you deal with space waste? So if you have many of these and they just break down, like what do you do?
Yeah, so the stuff that I've worked on has all been deployed in really low orbits where things sort of burn up relatively quickly and don't stick around and cause debris kind of problems. In higher orbits, you certainly have to worry about this sort of thing. I'd argue, though, without the super small stuff we're doing, people are already doing stuff that's maybe not super great in that respect, and namely it's Starlink. So yeah, I guess as a counter to like that, I would argue that one of the main motivations for doing small stuff is that it's cheaper and you can iterate faster, right? And Planet's a good example of this. A lot of the startups have been doing this, where you can afford to launch every year or every 6 months and put newer technology on orbit, and the design life of the spacecraft is much shorter, right? And so if that's the case, now you're not talking about putting things up in geo where they're going to stay there forever and be long-term problems. Now we're talking about putting things into like 400-kilometer orbits where their design life is a year to 2 years, and they're going to re-enter for sure. And it's sort of a self-cleaning thing. So I think there are, right, like a different way of looking at it is it's an advantage from that perspective, because you can put the things in lower orbits where they're guaranteed to clean themselves out. And that sort of ties into this, like, you know, quick iteration, design iteration, low cost of launch, all this other stuff, right?
400 kilometers, you've got a bit of a time constant there. With a small satellite, are they going to come in faster? You got smaller surface. Well, the surface area to mass, maybe, depending on how they're feathered, is
It's bigger.
It's bigger. So
yeah, right. It's like a length squared versus length cubed thing.
Yeah.
So when you shrink, yeah. So I mean, one of the things that was floating around in the lab I got my PhD in with Mason Peck 10 years ago was this idea of non-ablative reentry. Like for really small things, you can exploit that scaling. You get like this 1/r scaling of area to mass. As you get really small, it turns out you can reenter without getting hot and burning up. And this happens naturally. Sorry?
They float down like a feather in a way.
Sort of, yeah. Or like micrometeorites that end up in your gutters, right? So this happens naturally. We kind of know it. But we looked at this from an engineering perspective and tried to figure out what it would take to actually engineer that to happen. It's really hard. It's got to be like super, super tiny or super, super thin. And it's just really hard to make it happen with something that's smart.
But would these tend to come down faster than just
Oh, yeah.
So they'll clean out naturally, more naturally,
yes.
more quickly.
Smaller satellites stay up for less time. They end up having larger surface area to mass, and therefore, they drag pulls them down sooner. By the way, there are a few deployable drag enhancement devices that have been designed for satellite disposal as well, so that like when it has reached its design life, sort of pop out this parachute-y thing and it pulls your satellite down in weeks, say. From these low orbits.
And you didn't talk about thrusters at all.
That's right.
People play with little ion rockets in these things. Maybe you have some sort of a resistor jet if you have enough power, but of course that's just consumable. What kind of translational force would you look at in these if you wanted to change orbit plane or kick momentum with a consumable?
Yeah, so there's been a ton of work on this from a lot of different places. Paulo Lozano's group at MIT has been one of the major labs in this space of super tiny thrusters for small sats, and that's gotten commercialized in the last couple of years with this startup company as well. There's a couple other companies doing electric propulsion for small sats, like ion thrusters and this kind of stuff. And then there's another set of ideas that kind of grew out of the lab I got my PhD in at Cornell as well, which are these like water rockets, electrolysis rockets. So the idea being you want to circumvent the safety restrictions on these ride shares that don't allow you to have pressure vessels or combustibles. So you launch with a tank full of water in an unpressurized tank, and then on orbit you electrolyze it into hydrogen and oxygen and then combust it. That also got spun out and commercialized. There's a company in Seattle called Tethers Unlimited that's got sort of a commercialized version of that idea. So there's a bunch of ideas. I would say none of them are like are capable of really large delta Vs. They're sort of thing you might think about doing station keeping kind of maneuvers with, maybe up to like tens of meters per second, maybe 100 meters per second. So none of these is going to like fly you to the moon, say, but they might be able to do station keeping sort of things. Orbit maintenance.
Cool. Well, maybe just as a final word, what are some more applications that you're excited about for these distributed spacecraft for Earth and science?
Yeah. Okay, the ones that I'm like most into. So one of the ones that like we're actively pursuing right now, that I've been sort of interested in for like a decade, with one of my longtime collaborators, is this space-based wildlife tracking thing. And in some sense, it's like flipping the ChipSat concept around. It's essentially the same comms ideas that we used to close the ChipSat link, but the tags on the birds are sort of the ChipSats, We're sticking the receivers in space on small sats. The navigation techniques there are actually super old school. It's a Doppler-based navigation idea. So it turns out you can back out the position of an object or of a transmitter on the ground with a single Doppler curve from a single flyby of a satellite. You get this like characteristic S curve, right? It turns out this was figured out during Sputnik. It's like one of the oldest ideas in space flight. It was two engineers who were fresh out of grad school working at applied physics labs who like listened to Sputnik fly over, had this idea, went and did it in like a weekend, and then showed it to their boss, and it launched all of satellite navigation. It launched this program called Transit, which was the predecessor to GPS. So it's a cool story. Anyway, so that idea was done like back then, and then kind of got supplanted by different ideas for GPS, and kind of has not been done in a while because it's less accurate than the techniques used by GPS. But it turns out it requires way less energy per position fix. So it's advantageous if you care about doing stuff on tiny low power devices. So maybe it's a good idea for these kind of tags, and maybe for like IoT kind of devices more broadly. So that's kind of one of the things we're looking at. I mentioned the low frequency radio astronomy thing. I'm super into that. We have no money to do that. And then the other one, the wiggly arm attitude control thing, we have a proposal in the hopper right now to do that for small satellite telescopes for doing, right now the limitation on these small telescopes is the reaction wheels are bad, as I mentioned, because they're big, but they're also bad because they produce jitter. It turns out because they're spinning around at typically hundreds of hertz, these little reaction wheels, they cause hundreds of hertz level jitter in the telescope structure. On big telescopes, they mount these things on vibration isolation dampers and all this stuff. They also put in what are called fast steering mirrors in the telescope. So these are piezo actuated mirrors with control loops running at kilohertz to cancel out the 100 hertz vibrations from the wheels, which is kind of insane if you ask me. So when the external disturbances from the environment are like millihertz. So what we're looking at doing is using these deployable booms that can move, basically move much slower than the wheels would at the level of like, a tenth of a hertz. And so don't produce these high frequency vibrations that propagate through the spacecraft structure. So they get rid of the need for the fast steering mirror and dramatically simplify the whole design and let you do ultra fine pointing on a very small satellite. And that lets you do long exposures for looking for exoplanets and things like this on a much smaller telescope. So that's another small sat idea that isn't distributed, but is kind of, of this flavor.
It's amazing the length they go to on space telescopes to dampen the reaction wheels.
It's all from the wheels. Yeah. When I talked to some of the, so I talked to a guy who worked on Hubble and is currently working on JWST, who's at Johns Hopkins. And his whole job is like looking at high fidelity finite element models of the spacecraft structure and vibrations and how they couple from the wheels into the structure and propagate through the structure, and then how they have to do this fast steering mirror stuff. And it's absolutely nuts. And it's all happening at like hundreds of hertz to kilohertz. And I just backed up and looked at, we actually ran a Monte Carlo of a satellite in Earth orbit and all the natural disturbances. And the frequency spectrum, the power spectral density of all the environmental disturbances is below like 0.01 hertz. There's nothing fast at all.
Yep. It's like a mini Lego in its complexity. They don't have to go nearly that far down, but it's all about taking those disturbances out just because of the mechanics there. But then taking some inspiration from Dave, could you use high temperature superconductors and do a magnetic gimbal? Because then,
I think that stuff's awesome. There's some other ideas like that in the large space telescope space that I probably can't talk about. But yeah.
But if you could scale it down, then, and it may with high temperature superconductors, maybe you can make it smaller. And you wouldn't have the mechanical problem. Well, there's always some instability in the control, but the thing wouldn't have a mechanical joint. So anyway.
All right, guys. It was super fun talking to you.
This is great.
Feel free to reach out by email if you want to chat.
This has been phenomenal. So many of us are chatting on the sides, wondering how you get to work on so many cool things in the short period of time.
I don't get to work on them all. That's the... I get to raise money for them and then let students work on them now. That is my life. All right.
Well, thanks again for joining us and for sticking around a little extra. Nice.
Yeah, sure. See you later.
Thank you.